Okay, so starting on page 14 in the big packet. First of all, welcome back. Happy Friday. I just walked around and checked homework for the first time. That gives you a sense of how I check homework. If you don't have it on the day that it's due, I will take it one class late with no penalty at all. So even if you don't have it today, I can take it Monday. And to be honest, just because I know not everybody has the book just yet, I'll even take it Wednesday next week. But if you don't have the book, you want to get it ASAP. And until you have a copy of that book of your very own, use the one in the studio or on reserve in the library. Mo? We're not going to use the book in class. You don't need to bring it with you to this class. Good question. Okay. All right, so here we go. Today is class number 2, section 2.1. We're going to talk about average and instantaneous velocity. And I want to point out at this very early stage in our calculus course that the order in which we are covering the sections, you can see in this column right here, is radically different than the order that the sections are presented in the book. We did 1.1, that seems like a reasonable place to start, but right now we are jumping right to chapter 2. And then we're going to head back to chapter 1, and then chapter 2 for a few classes, chapter 3, and then chapter 4. And then you'll notice we go back and do lots of stuff in chapters you've already seen. And the reason that my colleague Caitlin and I completely shuffled the order of the topics in this textbook is that we wanted to get to this class right here, this one, polynomial optimization problems as quickly as possible. So the goal of these first 7 classes is to get there as soon as we can. Polynomial optimization problems are some of the hardest problems in calculus. And what we decided was that a lot of the really hard problems in the typical Calc 1 class happen in the last 3-4 weeks of the semester. And that's not so great for students to have all the hard problems happening back to back to back. And so we are going to try to space out the hard problems, and we're going to make a beeline to this category of hard problems. So that's why things are really out of order. But I promise we will get through everything that we're supposed to. Okay, just a couple of quick things before we jump in on page 14 of the notes. So first of all, not sure if folks have had a chance to do this yet, but if you log into our Moodle class, it will look like this. And I just want to point out a couple of resources here. If you click on this link to a playlist of videos, it will take you to a playlist which currently has exactly one thing in it. I record all of my classes, and if you click here, you will see the video of what we did on Wednesday. So I'm just going to play a small snippet of that here. And so if it's going to grow slowly, okay, so you can relive the riveting moments of Wednesday's class. Right now, this is useful if you miss class, but it's also useful if there was something that happened and you need to see it again, and you can watch it and you can rewind it and whatever you need to do. Okay, so it's always going to be here for you. This playlist will grow, and currently we're at 7 views, but this thing's about to blow up YouTube now that you guys know that it exists. Okay, all right, another resource I want to point out is right over here. This one here says class notes filled in 201B and 201A. So if you click on 201A, you guys are the A section, you will open up a PDF. And currently this is one of the pages of the PDF. So everything that I wrote on the smartboard on Wednesday is recorded here in color, including my lovely cross sections of our lake filling up. So what that means is that you don't need to feel the obligation to frantically copy every single thing that I write on this board. It will be there for you in PDF form, okay? I'm not going to post this after class every single day. It's kind of a little bit of a chore for me to do that. I post it after every Friday's class. But if you are desperate to see what happened after a Monday or Wednesday class and you can't wait until Friday, email me and I'll send you the PDF, okay? But every Friday, I'm going to update this thing, including today. So there are 2 sections that I'm doing of this course, A and B. You guys are A, but section B, the notes will look quite similar. Any questions on any of the resources there? Okay, super. So let's jump back to page 14. And we'll start up here at the top with our daily summary. In this class, we calculate instantaneous velocities and we connect them to tangent lines. Number 1, let's spend some time talking about the projects. Over the course of the semester, you will complete 6 projects plus 1 small project where you reflect on the semester. The first 2 projects were handed out in our first class and are due in about 3 weeks. These projects involve doing problems that are much more involved than typical homework problems. You'll have to do some reading for several of these projects. If all projects are encouraged to work with other students in the class, you are also welcome to ask me questions. You are welcome to ask faculty in the Math Studio questions. Any resource you want is fair game here. You guys are the best resource for these projects. Talking about calculus with a classmate is one of the best ways for you to learn calculus. Since the projects are so involved, it is highly recommended you try to stay on schedule with respect to the project timelines. Remember, those are on the back of the first page of the projects. Do not wait until the last minute to try to do the projects. There's a reason these projects are due in 3 weeks and not in 3 days. An upcoming class period will be devoted to checking in with each other and with your teacher on your progress on the projects. You will get the most out of that class period if you've been keeping up with the suggested timeline. Any questions on the projects? Okay, there's no judgment on my part here, but raise your hand. Oh, yeah, Mo. They're due one class apart. It's here on the back of your syllabus. The arbitration project is due September 28th, and the trucks project is the 30th. Okay. Other questions? Okay, so there's no judgment on my part. I just want your honest answers here. Raise your hand if you have not had a chance to look at either project just yet. You are not alone, I promise you. So a few folks have had a chance to open these things up. All right, hands down, it's fine. But hopefully you find some time this weekend. I've got that timeline for the projects laid out clearly on the backs of those first pages. And I'm assuming you're doing some stuff this weekend, especially if you haven't done anything over the last 48 hours on the projects, okay? It is I hope that the timelines are reasonable if you follow them. But if you wait until the last minute, they are very unreasonable to do, okay? All right, so number 4 says we're going to jump to the group activities first, and then we'll come back to the demo at some point. So the group activities start on page 15. And what you are going to do, not just yet, but momentarily, you're going to reintroduce yourself, write down the names of all the people sitting at your table. You are going to read the words. You are going to look at the graphs. The questions are all on the next page. Today's class is chock full with lots of calculus goodness, and so I need you to really motor through the questions on the next page so we have time to do the tougher stuff coming up this class, okay? So reintroduce yourselves, look at the pictures, answer the questions on the next page. I will call you back together at some point. Okay, so we're going to tackle this number 1 here in the demo, and as soon as we finish this little demo, you're just going to go back to the problem on the zombies that you were on, okay? All right, number 1, suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Let's estimate the instantaneous velocity of the ball at t equals 5 seconds. Instantaneous velocity of the ball at t equals 5 seconds. This is quite similar to the last question of the zombie problem, which not everybody saw, but the last question asks for the instantaneous velocity of one of these zombies 2 hours in or something like that. And so we're going to do the same idea here, but this is a falling ball. Here's a fact from physics. The height s of a falling object is given by this fancy formula. S of t, where t is the time, is 1/2 at squared plus v sub 0 times t plus s sub 0. What does a stand for? Acceleration due to gravity. What does v sub 0 stand for? The initial velocity. V is the velocity and the 0 is the initial part. What does S0 stand for? Initial height. S is our word for height or distance. S is our letter for height or distance. And again, the 0 is the initial, so initial height. All right, so let's see if we can write down our specific formula. Equals 1/2. Okay, acceleration due to gravity is just going to be one of these numbers that you either have memorized already or you're going to soon. What is it in meters per second squared? 9.8. Okay, so it's just a magical number that we're going to memorize. Times t squared, we're copying that guy, plus v sub 0 is the initial velocity. This ball is dropped. What is the initial velocity? It is 0 meters per second times t, just copying that t, plus s sub 0. S sub 0 is the initial height, 450 meters. So we'll put a 450 there. Equals. And now we'll just crunch some numbers. Half of 9.8 is 4.9. T squared plus 450. So there's our formula. It tells us the height of this object as a function of time. Just to kind of ground us in this formula, if we plug in, for example, t equals 5 seconds, let's just do that. That should tell us the height of the object after 5 seconds, s of 5 equals. So all we're doing is plugging 5 in. We'll get to you in just a second. We're plugging 5 in for that t. And somebody with a calculator help us out here. Crunch this number. And this will tell us the height of the object after 5 seconds. So how far off the ground is the object after 5 seconds? Do we have a number or a problem? That's the right answer, but that is not this answer. What is this here? 572.5? So anybody else get that? 572.5. 72.5 meters. So 5 seconds after we drop this thing, it is 572.5 meters above the ground, which is slightly troubling. What's the issue? Gravity's going the wrong way. Gravity is not 9.8, at least not according to our calculations here. What is it? Negative 9.8. Big problems if we have it as a positive. Okay, so let's make this as negative 9.8, negative 4.9, negative 4.9. Okay, and then Josh, I think you told us what the right answer is supposed to be. Okay, that's more reasonable. Better be something less than 450 after 5 seconds of free fall. Good? And it's important to just check little things like that, right? It's easy to miss a sign, but if you just do a quick reality check, you'll see there's a problem. Okay, so that's great. So now what we're going to do is we're going to estimate the instantaneous velocity of the ball at t equals 5 seconds. You've been doing this on the zombie problem. All we're going to do is focus our attention on an interval that either starts or ends with 5 seconds. So for example, suppose that I looked at this particular ball between 5 seconds and 7 seconds. We'll use our basic formula from physics, which says that velocity is change in distance over change in time. Yes? We're not using the letter D here. What are we using for distance? S. So change in S over change in T. So big fraction here. I said we're interested in the instantaneous velocity at 5 seconds. So it sure feels like 5 had better be one piece of our calculation. And I'm just going to kind of arbitrarily here decide we're going to look between 5 seconds and 7 seconds, and then we'll change the 7. But for right now, it's a starting place. So if I'm doing between 5 and 7 here, then what calculation goes downstairs for the change in time? 7 minus 5, right? Okay, so that is what we need to calculate. And we'll do that here. You're welcome to try typing this on the calculator, but I'm going to type stuff in a little bit faster than I'm expecting folks to keep up. But again, this is on the video, so if you miss any of the details, you can check it out later. Okay, so I guess what I want to do is do S of 7. So what does that mean? That means plugging 7 right here for this t. So negative 4.9 times 7 squared plus 450. And so the height of the object after 7 seconds is 209.9 meters. And so I could just plug that right in here. That's 209.9. We've actually already done S of 5. What is it? That's just 327.5. And we would subtract them, and that would tell us how far the ball had fallen over the course of those 2 seconds. And we divide by 2, and we'll have our average velocity. But we're going to change this 7. We're going to do a bunch of calculations here. And I don't feel like retyping this every single time. So we're going to be a little bit fancy here because the calculator can do some cool stuff for us. I'm going to go into the y equals menu. And again, not expecting folks to keep up in terms of typing. I'm going to type this formula in once. Negative 4.9. All right, I can't use t. I'm going to have to use x. X squared plus 450. So there's my formula. And that allows me to get away from typing this long thing. This is something that some of you maybe haven't seen, but if I go into vars, variables, oopsies, vars, and I scroll to the right to highlight y vars, and the very first option there, function, is the one that I want. I'll hit enter, and I see a list of all the things that were in the y equals menu. And if I choose number 1, hit enter, it brings y1 right there. Now you guys know function notation. We used S of 7 right here. That's our function notation. Okay, so it looks a little bit clunky, but y1 of 7 is S of 7. That's what it means. And so we're not going to be surprised here to get what number? 209.9. That's exactly right. And it's a lot easier to type this, given that I'm going to do this calculation many, many times. All right. Okay, the next thing to do is something like this. So we're going to do bars y1 of 7. So right now I'm just typing in this thing in blue here. Y1 of 7 minus bars y1 of 5 divided by 7 minus 5. And so that right there in one fell swoop is our average velocity between 5 seconds and 7 seconds. Negative 58.8 meters per second. Fair? Okay, but between 5 seconds and 7 seconds, a lot changes. And so how about we tighten that window quite a bit, and maybe we go from 5 seconds to, just throw out a number for me. What would be better than 7? 5.5 would be better than 7, right? What would be better than 5.5? 5.2, and 5.1, and 5.01, and we're just going to shrink in, shrink, 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 really, really close to, but never quite equal to 5. So let's try that right here. If I do second entry, it will retype everything that I've got. I'm going to do 5.1. So 5, and then I have to insert here so we don't type over stuff. So I'll show you. I typed in the 5, which automatically types over. Second, and then INS is right there in yellow, right above the delete key. It changes the cursor a tiny bit. Yeah. So we type in 5.1, it moves everything over. Game changer. I like that. Okay, so between 5 seconds and 5.1 seconds, the velocity here is negative 49.49. Great. And if we wanted to go between 5 and maybe 5.01, all I have to do is insert a 0 right here, and then a 0 right here. Insert 0 there. And hopefully we are honing in on a number that we're just going to guess. Anybody have a guess looking at these three numbers? Maybe negative 49. Like it might be perfect at negative 49. It's hard to know just by looking at 3 data points. Okay, that is good. Technically, we should have been looking on both sides of 5. Right now we're only looking above 5. But what other numbers should we be trying here? Like 4.99. Okay. So we can try that second entry. 4.99 in both places. And hopefully we get something comparable, hopefully still honing in on this negative 49 if that's our best guess. How does that feel? That feels pretty darn good. Okay, so let's just record a few of the data points here. And so we'll say something like this. Between, let's see, average velocity, I'm just going to kind of make up notation. Average velocity between 5 and 7, that was the, what was, anybody have that written down? Negative, is that what it was? 58.8, that sounds familiar. Okay, so that was negative 58.8, and then we did, I think we did 5 to 5.1. 5.1, and that was negative, yeah, I think that's right. And then I think the last one we did was 5 to 5.01, and that was negative 49 point, is it just 049? Great. And we also did 4.99. And so we just make our best guess. I'm just going to write the word guess, because we don't know yet technically, but the instantaneous velocity at 5 seconds, maybe negative 49 meters per second. It's the best we have right now. Fair? So we see like find average velocities over better and better intervals. Great. Okay, one visual that we can take a look at here is this guy. This is a piece of software called Geometers Sketchpad. I'll show some things on this throughout the semester. This formula right here for that purple parabola looking thing is right down here. It's negative 4.9 x squared plus 450. This is supposed to represent the height of the ball as time passes, okay? Right here, I've got this fixed point at 5 seconds. 5 seconds into this trip, the ball was 327.5 meters above the ground. Then I've got this green point over here, this varying point, and I'm going to take this guy and I'm going to move this thing. First thing that we did, the varying point has coordinates up here. First one I'm going to do is try to shoot for this guy to be 7 seconds, which was our first average velocity calculation. So it's not going to be perfect. I'll get you close. 7 seconds in, I think we said 209. Is that what we got? Yeah, so I'm not quite there. And then if you wanted to find the average velocity, well, it's the change in distance, which is this vertical distance, over the change in time. But hey, wait a second, a vertical distance over a horizontal distance is also known as what? Is a slope. And so I think it was negative 58 point, I don't remember, 8, negative 58.8. But that is the slope of that line right there. What's the name of a line that connects 2 points on a curve? Starts with an S. That's a secant line. Secant line. So the slope of the secant line is actually exactly that average velocity. And how can I make this this guy right here closer to the instantaneous velocity at 5? We're going to take this varying point, we're going to bring it closer. I'm just looking up here, trying to make it about 5.1. Not going to be perfect. How about there? And this is pretty darn close. I think we said negative 49.49. And it is still a secant line, but gosh, it's getting hard to tell that these are two different points because they're so close to each other. I'll try to make that a little closer to 5. That's probably about as good as we're going to do, 4.99. Indeed, really close to negative 49. If indeed those 2 points are right on top of each other, then that line should disappear because the line is defined by connecting those 2 points. But we've got another word for that particular line as long as it doesn't disappear when it really is just the 1 point. That's a tangent line. And a lot of our early calculus stuff is about tangent lines. And that's what we're after here. Okay. So coming down here, number 3, good definition. A secant line is a line that goes through how many points on a curve? 2. 2 points on a curve. Here's a poor definition. A tangent line is a line that goes through 1 point on a curve. That is not a good definition. That is a very much flawed definition, but it's as good as we have for right now. We'll get something better soon. 4, what's the graphical interpretation of average velocity? We said this a minute ago. Slope of what? Average velocity was slope of which one? Was a secant. 2 different points. Slope of secant line. Number 5, what is the graphical interpretation of instantaneous velocity? Slope of a tangent line. Okay. All right, so number 6, you're going to pick up where you left off with the zombies. If you finish the zombies, you're going to number 9 on the next page. We're going to come back together in the last 10 minutes of class. Let's see how far you can get. All right, so we're just going to go through some of the highlights. I know not every group got all the way to the end of this activity, and that's okay. But everybody's back here. Come on back together on this graph. Okay, so we introduced this H business. H was this horizontal distance right here. H is the horizontal distance between our fixed point, which was at t equals 5 seconds, and our varying point, which was someplace in this picture off to the right, but it could be off to the left. And if we want to take that varying point and move it very close to the fixed point, which is what we did on that, worksheet, what are we sending H towards? Not 5, but 0 in this case. Yes, we want to send t towards 5, but H is this horizontal distance, and we want to send H towards 0 in order to move that 1 point, the varying one, close to the fixed one. And so we go through our calculation. I'm just going to circle it here. This is just a change in distance over a change in time. It's our basic average velocity calculation. S of 5 plus H minus S of 5. That's the change in distance, change in height, over 5 plus H minus 5. I'm not going to go through, but hopefully if you haven't had a chance yet, later on you'll confirm all of these calculations are sound. And we end up with this thing in simplified form. And then in the very last step, we say, okay, those were all average velocities up there, but instantaneous velocity, it's the same exact thing, except we said we're going to send H towards 0. And we'll talk in detail about limits next class. But for right now, hopefully we just got this intuitive idea. Send H as close to 0 as possible. Technically, we can't make H equal 0 because all of a sudden the secant line doesn't exist anymore. And in fact, if you plug 0 for these h's here, what happens? You can't divide by 0, and maybe even funkier than just dividing by 0, what do you get on the top when h is 0? Is also 0. So it's like 0 divided by 0. Yeah, not quite sure what to do with that. Certainly we can't type it in the calculator. But what you can do is pick numbers close to 0 for h, for example, 0.1 and 0.01, and maybe some negative numbers too, negative 0.01 and negative 0.1. And you're welcome to plug any of those 4 numbers into this red circled formula, and you will get calculations out, and you will make your best guess looking at the data, okay? Great. On the next page, just one more time, I'm going to highlight this thing up here circled in blue. S of 5 plus h minus s of 5 over 5 plus h minus 5. That is just a change in distance over change in time, yes? What do you get on the bottom when you simplify? You get h, right? 5 plus h minus the 5. I'm going to change these 5s to something more general in a moment. I'm going to change it to the letter A. And so this is going to become an s of a plus h minus s of a. 2 5s both become a's. But even if these 5s both become the more general a, what do you get on the bottom still? You still get h. So the bottom is going to be h no matter what. So on the very next page, number 1, the instantaneous velocity of the function y equals f of t. This used to be s a moment ago. At t equals a, that a used to be 5 a moment ago, is given by this crazy formula. Again, I'll write on the previous page. It said s of 5 plus h minus s of 5 over h. It is just slightly more general right now. The 5s became a's. The s's, which was a height function, became a just generic f function. Any old function you want, still going to send h towards 0 every time. Note that this fraction is called the difference quotient. You might have seen that phrase someplace else. It might be in your book. Number 2, when we talk about slope of a curve, we mean the slope of a tangent line to that curve. Slope of a curve now always means slope of a tangent line, right? Slope is only defined for lines, change in y over change in x. But if it's a curve, it's got tangent lines all over the place. And so you draw the one you want and you find its slope. What does the slope of the tangent line represent? A moment ago, it represented instantaneous what? Instantaneous what? Velocity, but that was specific to our height problem. In general, it just represents an instantaneous rate of change. It doesn't have to be a change in distance over time. It could be maybe a population of ladybugs, which grows and shrinks. And so you could have the instantaneous rate of change of the population over time. You could have money in your bank account, which hopefully is growing, but sometimes it shrinks, and that has instantaneous rates of change, right? Okay, number 3, a problem from last night's reading. Suppose Ian throws a grapefruit straight up with an initial velocity of 100 feet per second from a height of 6 feet. Without a calculator, we'll find the velocity of the grapefruit 1 second into its flight. Here we go. S of t equals, it's the same 1/2 at squared, 1/2. On the dropping the ball problem, we had a negative 9.8. That was when we were doing meters. This is feet. For feet is 32. We're just going to call it negative 32, okay? Negative 32 feet per second squared. T squared plus, what's the initial velocity? It's 0 if we drop it, but that's not what's happening here. So this one, I'm actually throwing it up at 100 feet per second. So that's 100 times the t plus s sub 0 is the initial height. What is it? 6. So I throw it kind of right here from top of my head at 100 feet per second. Let's just smush the first 2 numbers together. Negative 16 t squared plus 100 t plus 6. Okay, so let's put pencils down here because I don't have quite enough time to do this and have you copy along. But this PDF will be posted shortly after class, okay? All right, so instantaneous velocity, looking 1 second into the flight. Here we go. The formula that is right up there at the top of the page is this f of a plus h minus f of a divided by h. And in the front is this funny limit as h goes to 0. What's the specific number a in this particular problem? Is 1 second in. That's what we're interested in. So 1 plus h minus f of 1. Up at the top was this general f, but here we're back to distance functions or height functions, okay? All right, a little bit of algebra before we start doing calculations. 0. S of 1 plus h. Let's do the easier part first. S of 1. If I plug 1 into this entire function right here, negative 16 times 1 squared plus 100 times 1 plus 6, what is that? Is that 90? Somebody help me out. 90? No? Okay. Just plugging 1 in. I'll copy the h. The first part is the trickiest part. S of 1 plus h. All of the t's become what? 1 plus h. All the t's become 1 plus h. So we go negative 16, 1 plus h squared, plus 100, 1 plus h, plus 6. I'm going to highlight all of that is that. That 90 is S of 1. Okay? That's the tricky part. All the h's became 1 plus, all the t's became 1 plus h. Here we go. Now, we got lots of distributing to do. Bear with me here. I think we can crunch this through. 1 plus h squared, 1 plus 2h plus h squared with the negative 16 in the front. Plus, we'll distribute the 100. 100 plus 100h plus the 6 minus the 90 divided by the h. That negative 16 is going to get distributed, and then we're going to combine terms 2 steps in 1 here just because we're short on time. Limit h goes to 0. Negative 16 there. Plus 100, that's 84. Plus 6, that's 90. Minus 90. 0. Oh, isn't that just lovely? Next part, negative 32h here, plus 100h, I think that's 68h. I don't see any more h's. 68h. I've got some h squareds. Negative 16h squared, nothing else. Divide by h. What can I factor out on the top? We can factor out the h. I think you could also factor out, I think somebody said 4. Wait, is that right? 60? Yeah, 4 goes into both, but to be honest, who cares? It's really the h that's the key. We're factoring that h out. Here we go. 68 minus 16h divided by h. Limit as h goes to 0. Those h's right there, what can we do? Cancel them. The most satisfying part of this, not that this problem wasn't satisfying to this point, but that right there is the whole ball game, because now it is really easy to look at that without a calculator and say, hey, I know if I plug in numbers for h that are very close to 0, what is that going to get very close to? 68. By plugging in h is 0.01 or 0.0001. And without a calculator, it's just 68 meters per second, right at 950. Fantastic. We'll see you guys on Monday. Have a great weekend.